Good afternoon. Welcome to the colloquium. I have to start us right at 3:30 today because someone has the room booked after us. I'm very happy to introduce Therese Biedl, who's a professor in the computer science department here at Waterloo. She received her PhD from Rutgers University under the supervision of Andre Boros. So her main research interest is algorithms for geometric problems, including computational geometry and planar graphs. So the floor is yours.
Thank you for the introduction. And yes, this is joint work with Ignaz Rutter, and the backstory of that is that I was recently on a sabbatical over in Europe and went to a workshop in the middle of nowhere in the Czech Republic. And in order to get there, the organizers organized a bus that went from Prague to that middle of nowhere, Nova Luka specifically it's called. And I happened to sit next to Ignaz on that bus. So I asked him, so Ignaz, what have you been up to lately? Away, you chit-chat away, thinking nothing will happen. And he says, oh, I have this logic colleague of mine, and we've been chatting about MSOL, and I've really been exploring that. I'm like, perfect, because I have this graph drawing problem, and I really need somebody who can do MSOL so that we can phrase that in MSOL. You will see what that means, but yes. So by the end of the bus ride, the paper was basically done, except for the finer details that need writing up, which we're still working on, but this talk will help me actually write the paper, I hope. All right, so this talk is about two things, planar graph drawing and MSOL, and then where they meet in the middle. I am not assuming that you know much about either one of these topics, so a good part of my talk will be simply spent on reviewing what is all this stuff, which also means that for the main result, which is sort of more in part 3 and 4, I won't have enough time, which is perhaps a good thing, because as I said, details still a little bit to be worked out on. But let's start with this review. So what are planar straight line grid drawings? Well, let's start with something you hopefully all know. Let's start with planar graphs, and you should know those are simply the graphs that in some form or another, with curves or not, you can draw in the plane without any crossing. And just to get rid of trivialities, graphs are big enough and connected and simple in this talk. And all the graphs are planar. I will not talk about non-planar graphs except perhaps on the open problem slide. All right, what you probably perhaps have heard of is that, yes, I allow curves in this definition, but I didn't need curves. So multiple people repeatedly have proved that actually, if you have a planar graph, you can draw it so that all the edges are drawn as straight line segments. And that's a pretty old result, and as I said, proved repeatedly by many people. Now, unfortunately, as you see in this drawing, as it switched from the nice and curvy to the straight line drawing, these drawings are not ideal in some sense. These two vertices are awfully close to each other. And the way these particular proofs at least work, that's almost in the nature of things. You kind of recursively fiddle in things somewhere in the kernel of some star-shaped polygon, and they might end up being pretty close to each other. So not a very good resolution. This got fixed quite a few decades later. And in what is probably one of the foundational results of the whole graph drawing area, two teams of researchers showed that, in fact, what you can do for a planar graph is you can draw it in the plane with straight line segment, and you can furthermore demand that your vertices have integer coordinates. I will simply call that they sit on a grid. So all the coordinates of all the vertices are integers, and that grid is not too big. Specifically, the size of the grid, both the width and the height, is linear in the number of vertices. And it's not even a ridiculous linear. It's either n by n or n by 2, and depending on which author set you take here. So yes, we have beautiful drawings on not too very big grids, but also not very small grids. I mean, order n by order n, you wonder perhaps I could do less than that. Before we talk more about that, disclaimer from now on, when I say drawing, I mean this kind. So from now on, it's always a grid drawing, it's always a straight line drawing. I don't talk about other drawings. All right. So what I wonder about is how small can we make these drawings? And in particular, the aspect of the drawing that I want to make small is what I call the height or the number of levels, by which I really mean the smaller dimension of the grid. After rotation, you might assume that the height is the smaller of the two-dimensional or the not bigger one. And I would like to keep that one really small, and that's what I call the number of levels. But I have a tendency to use the word layer rather than levels. They mean the exact same thing. It should be called level, but somehow I always say layer. I don't know why. All right, so this talk is about how small can you make that? Or in other words, I'm looking at the following decision problem. I'm giving you a graph. I'm giving you an integer h. Do I have a drawing, which as always means planar and integer coordinates and all that stuff, on h levels, or off height h, completely equivalently the same thing. That's the main thingy I want to talk about. To get used to this a little bit more, here's a graph. What do you think? How many levels do you need, or what height do you need for this graph? Now this picture, even though it has curvy lines, it already kind of suggests a layout of these vertices, and if you do a little bit of counting, you'll probably see that's on 6 levels. And I claim that I need 6 levels. You can't do less than 6 levels for this graph. Why is that? I have highlighted them in red, but I don't think we see colors very well on this screen. You see here 3 triangles, and these triangles are what I call stacked. One triangle is inside the others, inside the next one, and so on. Or put the other way around, one side is outside the next one, outside the next one. And I claim that to draw such a thing, I simply need 6 levels. Why is that? Well, each stacked thing that is here needs to go around the entire previous drawing. And to go around the entire previous drawing, you need 2 more levels. So I need 6 levels for this beast, and I can draw it on 6 levels, so that's the optimal height. Make sense? You believe me? You're happy? Good, because it was a complete lie. I can draw that graph on 2 levels. Huh? Didn't I have a good argument here? The question is really, what do I want of my drawing? There's really 2 questions going on when I talk about straight line height. The question is, do I want to draw it any which way I please? That's what's happened on the right. Or do I have to more or less preserve the drawing you gave me? We call this an embedding, and I will at some point later talk about what exactly I mean by embedding, but roughly speaking, you gave me a vague drawing, and I should respect that. And that makes a difference. You see it in this example. On the left, if I have to keep the 3 stacked cycles as stacked cycles, I need 6 layers. But if I'm allowed to rearrange, then I can do it on 2 layers. So it makes a difference. So really, I have 2 questions here, not just one problem. I have 2, which I will simply illustrate with a substring, either fix, which stands for fixed given planar embedding, or a variable, use the best possible embedding. Some of you may know for a 3-connected graph, it makes no difference. But in general, for graphs that are anything and might not be 3-connected, it can make a difference. All right? So what do we know? This is my problem, and I will kind of give you answers or part answers for both of them, both versions of it. So this problem is a decision problem where h was how many levels do you allow me? So let's knock off the really easy cases of when h is really small. When you give me 1 level, I mean, come on, you know what your graph has to look like. That's it. So your graph has to be a path, or a union of paths, but somehow I assumed I'm connected, so then it's just a path. 2 levels are a little bit harder. Graph has to be outer planar, whatever that may be, and very structured, and it has to have path width 2, if you know what path width is. But yeah, we can still test that somehow. From 3 on, things got messy. So Cornelsen, Schank, and Wagner tested it for 2 and had some partial results for 3, but didn't quite do it for 3 layers. So small values of h seem doable. The other thing that is doable is if my graph is pretty special. So Mondal et al. Said for a tree, they can always do it. This is in the variable embedding setting. And then there's a graph class called the 3 trees, which I won't define, but these 2 here are 3 trees. And again, for those, they can do it. Basically, graphs that have a nice enough structure that somehow you can, by dynamic programming, somehow kill the beast. It boils down to. But it's not obvious that this works. And if I phrase it that way, you can probably guess what the next bullet will say. In general, we have no idea. So if it's an arbitrary graph and an arbitrary h, I don't know how to compute the height, the minimum possible height. And so you probably expect that now I say, because it's NP-hard. Actually, I don't know that one either. I don't know whether it's NP-hard. It's one of the things where everybody thinks it's NP-hard, because basically in graph drawing community, pick your favorite problem, it's NP-hard. With very few exceptions, but the vast majority of problems are NP-hard, so it ought to be NP-hard, but none of us has found a proof so far. I have certainly been trying. Lots of related questions are NP hard, but this particular one, to my knowledge, has never been proved NP hard. If you have an idea how to do that, please talk to me. I'd love to have an NP hard test. All right, so the rest of the talk will quietly assume it's NP hard, but we don't know. All right. I'm omitting one very important result, which, yes. As of 2004, the status was H equal 1 easy, H2 doable, H equal 3, maybe. And people were working on 3 and maybe 4, and then came a breakthrough result that killed it all. Because one rather large group of authors, including 2 names that might be familiar for those of you that are from the CS side of the non-existing bridge, proved what? It's actually linear time for all constant H. Or what more specifically they proved is that there is an algorithm that gets this as input and checks whether the height is at most H, and the runtime is what they call fixed parameter tractable in H, which just stands for its polynomial when you look at the n aspect of it. It depends in a hilarious fashion on H, and we just write function of H, and we hide what that function is. I think in their case it was something like 2 to the 2 to the 2 to the 32 H cubed, or something like that. It's ridiculously big, but it's independent of n, so as long as your H is a constant, that gives you a linear time algorithm. All right, so fantastic result. We know it for all constant H. I won't have time to review this, but let me give you a flavor of how they did this. And the way they did this is actually first to appeal a result that was in some form or another known a couple years before that, which I already hinted at when I talked about height 2. If you have a planar straight line drawing of height h, actually it's true even if you're not straight line, fine, whatever. If you have a planar drawing of height h, then the path width of that graph is at most h. Now, I suspect that in this crowd, most people have actually seen the path width. If you haven't seen the path width, don't worry too much about it. We won't need the details of the definition, so I won't even bother giving it to you. It's some sort of graph parameter that is of high interest to a lot of people. And so if I have a drawing of small height, then some aspect, this path width, whatever exactly that is, must be small. Why is this useful? Because you can take the contrapositive. If the path width of my graph is big, there's no way it has a drawing of small height. So if you wanted to answer, does my graph have a straight line drawing of height h? The first thing you do is you compute its path width. Okay, we don't quite know how to do that easily, but actually approximating the path width is fine too. Like give me a 5 approximation of the path width. Still, as soon as you realize that the path width is just really big in this graph, you can abort and say, no way, it doesn't have a drawing of small height. So for the rest of this talk, whenever I talk about straight line height, I might immediately restrict to graphs that have small path width. And that's nice. And now, those of you that have seen path width before, what do you do algorithmically if you have a graph of small path width? You do dynamic programming in the corresponding path decomposition. And again, if you haven't seen path width before, then just take that as a black box. But if you've seen path width before, dynamic programming suggests itself, and the only thing that you have to specify is what on earth are the subproblems that are defined at every part of the path decomposition, and how do I fiddle them together. Takes them a good 20 pages to explain what the subproblems are and how to fiddle them together. Basically, it can be done, but the subproblems are somehow this. I will not explain this picture, but they're complicated, and the fiddling together is not at all easy either. So it can be done. I wouldn't say it's my favorite algorithm. It's a fantastic result, don't get me wrong, but it's not an algorithm I would want to implement. So, end of what I will tell you about this algorithm. It gives you a rough idea how it works, but I didn't much like it. Why did I not much like it? First of all, it works for the variable embedding setting. This is kind of snuck in under there somewhere, but it does not care about the embedding that you give me. It just picks whatever embedding, basically tries them all implicitly. Could I adapt it to work on the fixed embedding setting? Really not clear. The other thing is that planar straight line drawings are one thing, but what I really love is something called orthogonal drawings, which we'll get to far towards the end of the talk somewhere. And can I adapt this to do this for orthogonal drawings? Not clear. Probably. But you have to do, in order to do any kind of adaptation, you have to do a deep dive into the dynamic programming formulation, understand really what this picture means, and then modify it so that these subproblems return false if it doesn't satisfy whatever other restrictions you want to put on. It's really not easy to adjust this result, as nice as it is, to slightly change scenarios. A few have been done, but if you want to do anything, you basically have to redo the entire dynamic programming stuff because you've changed the subgraphs, subproblems ever so slightly, so you need to re-argue that it all can be put together. Painful. So here's the goal. How about I do this differently? So, not that I don't like that algorithm, but I'd like a different one that's more flexible. Here's the main idea. Remember, we know, or in general, I only look at graphs where the path width is small. Now, if you don't know path width, then you also probably won't know the other one, and if you do know path width, then you will know the other one. There's another parameter called the tree width, which is upper bounded by the path width. So if the path width is small, then the tree width is even smaller, right? So I'm going to switch from path width to tree width. Why will I do that? Because if you've ever heard anything about tree width and algorithms, then you've heard that as soon as you have graphs where the tree width is small, all sorts of problems suddenly become polynomial that were NP-R'd otherwise. And the reason why that is feasible is that there's a rather famous theorem by Courcelle, by now over 30 years old, that says if you can express your graph property in this MS formula, whatever that is, we're going to have to talk about that. But if you can somehow express your graph property as an MS formula, then testing whether a graph has that property is fixed parameter tractable. And now I just have to tell you fixed parameter tractable in what? In the size of that formula plus the tree width of the graph. And the formula we will normally set up so that it has constant size, or at least some size that's independent of the number of vertices, so hopefully that is small. So basically what I'm saying is, if the tree width of my graph is small, then I can test this property in polynomial time. So step one will have to come, what is MS? And then the other one, my goal was to find a fixed parameter tractable for straight line height. So somehow I need to express, does this graph have a drawing of height h in monadic second order logic, whatever that may be? And this is not at all obvious how to do that. So this is what's going to keep us busy for the next little while. Questions about graph drawing, because we're about to switch to part 2. Forget everything about graph drawing. Now we're going to talk a little bit about MSOL. And as you probably saw from the intro, I am not really the super world expert in MSOL either. But I think I'm starting to understand it. One gets there, one gets used to it, and one starts to like it after a while, even though in the beginning it's rather strange. All right, so what is it that we want to do? We somehow want to build a logic formula such that a graph has a certain property, so the logic formula will depend on that property, that is true whenever that formula is applied to a graph. The logicians call that G models that formula, but I'm going to avoid that term. Just think of it, the formula is true. Applied to G? Yeah, let me explain what you're allowed to do. So my formula has variables, which can be either individual objects or sets. My formula can use all the usual Boolean operations, negation and ANDing, and we can quantify, so for all. And of course, once you have these guys, you can derive all sorts of other Boolean operations. So all the usual Boolean stuff, that's all allowed. And then my formula can occasionally say, does the following hold? And that's what we call a predicate. And here's the predicates that I'm allowed to use. I can obviously ask, is this object that I have here in this set? That's a useful thing, so is X and E. And then come 3 more that are dependent on the graph that you feed it. So these predicates depend on some graph that we're talking about. And that's where this, when applied to G or G models, the formula comes from. When I'm using this particular graph G to answer these questions. So things I'm asking is it a vertex? Is it an edge? And is this vertex incident to this edge? And that's actually all I'm allowed to ask about the graph. Nothing else. Everything else you want to ask about a graph, you have to derive. Luckily enough, we can derive a lot. And very soon I will derive a few things, and then we'll use those as subroutines later. So it sounds very limited, but we can build up things pretty quickly. If we happen to have any experts in MSOL in the room, I'm using MSOL too. There is an MSOL 1, never mind what the difference is. I'm using MSOL 2. All right, let's do an example. Actually, we will do 4 examples, but let's do a baby example to warm up. My property should be that the graph has a vertex of degree 1, which, is almost the easiest question you could ask of a graph, but it'll show you that if you really want to write it out in all detail in the MSOL, you'll go nuts because things get so long so quickly. So what does it mean to have a vertex of degree 1? Well, first of all, I have to have a vertex. So there exists some V that is an element of the vertex set, which I'm allowed to ask. All right, I have a vertex, that's good. Now that vertex better have an incident edge if it has degree 1. So there exists an incident edge. So there's an edge, or there's an E, which is an edge, and which is incident to my vertex. Very, very soon I will just write there's an edge, because we know how to do this. But this is how you do it formally. So that is degree at least 1, good start. And now we just need to say, and not degree 2. Or in other words, if I have 2 that are incident, then they'd better be the same. So if I have 2 edges that are incident to V, and here I'm already starting to cheat and just give you what we had earlier, because you know how to write that now, and it makes it so much easier to read the formula if I write English and not all that existential and is member and so on. All right, so that has a vertex of degree 1. That was perhaps a little bit easy. Let's go one step up. K-coloring. Probably quite familiar to a lot of you, the usual K-coloring question. I want to color my graph with K-colors so that at no edge do I have the same color at both ends. So standard K-coloring problem. All right. The trick here is to change your mindset to work whenever you can in sets. MSOL works well on sets and items in a set, and not so well on assigning numbers or colors or anything like that. So we will phrase, please give me a coloring through sets. Here's what's going on. Don't look at the left, it looks terrible. Look at the right first. I want to pick K sets that are vertex sets and that cover all vertices. That would be good, right? Every vertex should get a color, and they should probably be disjoint. I don't really want a vertex to have 2 colors. As it turns out, it wouldn't hurt, but let's just demand it. And then for every edge, I want that the ends are in different sets. So if you phrase it that way, that's pretty obvious to you that that's equivalent, and then you have to just realize each of those is pretty easily expressible in MSOL. Existential quantify my sets. I want that they're vertex sets, so for every vertex in V1, or for every item in V1, I want that that's a vertex. Oh, in the future, I'll just write V1 as a subset of V, now that you know how I do that, and then I do it for all the others. And I don't want to write this down K times here because that's really annoying. So for our convenience, I will allow you to use something like a big wedge or a big V. But in reality, in the formula, I would write this down K times. This will be important in a moment. All right, and then in a similar way, they cover and they're disjoint. What do I do for disjoint? I just look at any 2 sets, and I say that if you're in one, then you shouldn't be in the other. Yes?
Like there's no concept of function in this language?
There is currently no concept of function. You can, of course, define yourself whatever and then use that as sub-predicates, but as given, no. Yes?
Is equality a predicate in MSOL, or is it
equality of what? Sets?
or equality of anything? Like, for instance, earlier we did equality of 2 vertices.
That is a good point. I think it is in it. Yeah. Of sets, you can even express it, but for items, I think we need to allow that, yes. All right, just one thing to point out. Somewhere in that Courcell's theorem, I talked about the length of the formula, and principally that is what you think it is. How many characters did I need to describe that? You just have to be a little bit careful when I talk length of formula, when we have things like this big wedge here. Because this is just a convenient shortcut for humans to read it. This is not something that's actually allowed in MSOL. I'm just doing that because I don't want to write K-squared items across my page. But this counts as K-square items that I've written here. So the length of this formula is proportional to K-square. Still, what that means is by Courcell's theorem, we can solve K-coloring. In time, what? Well, the right-hand side is an n because Courcell's theorem had an n there. And then the function depends on my k because it depends on the length of the formula, which depends on k square, and the function might as well absorb the k square. So it's a function of k, and of course of the tree width, because Courcell's theorem always needs the tree width. If this was entirely new to you, then take at least this slide home as something to have learned from. Whenever you tackle a new problem, quickly check whether you can phrase it in MSOL. Because if you can, then you have immediately a little result, which is not exactly groundbreaking, but still worth mentioning, that for all graphs where the tree width is small, you can solve that in polynomial time, in fact, in linear time. So, worth knowing about. And as I said, one gets used to MSOL, even though in the beginning, when you look at the left, that's overwhelming, but on the right, I hope it's okay. Let me show you some things that get tricky in MSOL, because not everything is as easy as K-coloring. K-coloring is really easy by local standards. So example 2 is a problem I made up. I don't know whether anyone has ever studied that. It's the same as K-coloring, except for bizarre reasons. I now want that if you look at the color differences at the 2 endpoints, that should please be odd. Whereas for K-coloring, it should not be 0, but now it should be odd. Why not? Who knows? Maybe someone needs that problem. I have no idea. So what do I want to do? I want a vertex partition, and allow me to write vertex partition. We know how to do that from the coloring problem, right? And then I want that for every edge, the difference of the colors is odd. But I'm subtracting here, and you haven't seen any sort of addition or subtraction or arithmetic symbols. And then I'm saying it's odd, so that's modular arithmetic. So how on earth do you do that in MSOL? So here's a pitfall. In general, MSOL does not do arithmetic. There might be versions of logic that allow you limited. This one, straight out as MSOL, no arithmetic allowed. Having said that, if the numbers that you do arithmetic on are in a pretty small range, and especially if they come from sets, then you can do some trickery and effectively do arithmetic. And I will show you how to do it on this particular example, and I think then you can see how you can do that in general. What do I have here? I have these vertex sets, and the numbers that I'm talking about are the indices of the vertex set. So what I'm going to do is I will simply write myself down all the pairs of vertex sets that I'm okay with, because the difference between the indices is odd. If you want to see a specific example and you sit really far front, then you can look down here where I tried to squeeze it in for k equal 4. But it's getting outlandishly big, really, in a hurry. But basically, just you look at all the pairs of indices that are okay for whatever operation you're doing. And then you're saying, okay, and for one of these pairs, my 2 vertices must be in it. And in a similar way, I could say, be one bigger, or whatever operation you want on these indices, I can express that. But it does very much need that I don't have too big indices, because this blows up the size of your formula, right? In the way I have here, it was a binary function with 2 parameters, so then it's k squared. If it had 5 parameters, it's k to the 5. So be careful with that. You want that those numbers are small. But I can do arithmetic as long as the numbers are small. Right? Third pitfall, or example, Hamiltonian path. Again, a problem we all know and love. I would like to find a path in my graph that visits every vertex exactly once. What this example is supposed to illustrate is that sometimes you just gotta change your mindset what you're looking for. Because your first instinct would probably have been to, well, give me an enumeration of the vertices, v1 up to vn. Bad idea, because the moment you have written down those n variables for these n vertices, your formula has length n, and we don't want that. Because the runtime depends with this f through the length of the formula, and we don't want that to be too big. So not that, doesn't work. Well, maybe you say I didn't really need the explicit vertices. Maybe it's enough to just say there's some permutation of the vertices. And hide behind that somewhere there must be the thing. Yeah, with that the formula would be short. The problem is that you cannot express permutation in MSOL. And the experts in MSOL have actually not just that I don't know how to do it, they have proved it can't be done. Don't ask me how it works, I'm not an expert in MSOL, but yes, it can be shown that cannot be done. So no, sorry, no permutations. I can do Hamiltonian path in MSOL, and therefore it is polynomial in graphs of bounded tree width, by totally rephrasing what it means. So let me convince you, and I hope this is obvious enough, that having a Hamiltonian path is the same as to have a subgraph that visits all vertices, it's a spanning subgraph, has no empty cut, so it's connected. There's 2 vertices of degree 1 because I wanted a path, not a cycle, and all the other vertices have degree 2. And that's the same thing, right? But all these things, spanning we've kind of seen, we cover all vertices. Degree we've seen, I haven't gone over empty cut, but it's pretty easy to phrase there's no empty cut. For every subset of vertices, there is an edge that has one end in it and one end not in it. You can phrase that. So, yes, Hamiltonian path has one, but if you try directly from the way you think of a path, you might have gone a little bit astray. So, message, if your problem doesn't like you and doesn't like MSOL, try revising the problem into something entirely different. Questions about MSOL? I could talk forever in examples, et cetera, but as I said, I'm A, not the expert myself, and B, I wanted to get to the stuff that's actually new. Everything so far has been reviewed. So, questions? All right, let's get into something new. So what is the goal? What I want to do is to convince you that this problem of computing the straight line height, if you give me a fixed embedding, is MS expressible. Brief reminder, what was the straight line height? You give me the graph, the height, and the embedding. I'm generally going to call the embedding M. It stands for map, at least in Courcell's mind. So he always calls it M, so I'm copying that. And then I need to find coordinates, basically, which for the y coordinates corresponds to the levels, and they're small, but the x coordinates can be anything. And then I need to compute the straight line drawing out of it, and that shouldn't have crossings, and it should reflect M. One of these 4 bullet points is easy. See which one?
The first one is just subsets.
The second one, I think, but yes, the assignment of the levels is really easy.
Yeah.
Yep. Why is that? It's basically a k-coloring problem, right? Basically, my levels between 1 and h is like coloring the vertices with which level they ended up. Except that I do allow horizontal edges here. Actually, in a moment, we will disallow horizontal edges, but yes. It's basically k-coloring. This is easy. Everything else is not easy. And yeah, time-wise, I don't have much time to talk about. But for example, how on earth are you going to test crossing if you don't have arithmetic and you don't even have the order of the vertices within each level? Like if I at least had the permutation of where the vertices cross the levels or something like that, and I could quantify over that, life would be better. But I don't have that. So I really don't know how on earth I express crossing. We're going to have to find a formulation that doesn't use test whether there's a crossing. That just can't be done. And what is this planar embedding anyway? All right, so that's the goal. Let me start by reviewing again what my input is. It was already, of course, here, but let me remind you what that all means and tell you a few things about it that are not quite standard. So what's my input to input? I mean, it's not an algorithm, it's a formula, but what predicates do I assume that I can use? So I'm given the graph, obviously, and these are not supposed to be the same color, but the projector obviously thinks they're the same color. Fine. So I'm given a graph and all the usual predicates that come with the graph that we've seen before, that's all fine. There's one little thing here that I will mostly sweep under the rug, but I need to store my graph in a slightly more complicated fashion than just your typical graph. Because in your usual graph, an edge has 2 endpoints. And for reasons of explaining things easier and not writing complete nonsense, what I want is that every edge has 1 endpoint. Which sounds a little bit weird because I can't change my graph that way, but actually this kind of trick gets done in many places. You can replace every edge by 2 edges, and one of them belongs here and the other one belongs there. And they talk to each other. So that really, in some sense, it's 1 edge, but each of them has a dedicated endpoint. And whether you do that by subdividing or by replacing in the 2 directions or something like that, it's a known trick. Also, don't sweat this much, not very important. I will just write a few formulas where I will talk about the endpoint of an edge, and this doesn't make sense unless I do this trick. All right, so that's my graph. Then I'm given my h, nothing special about it. The goal is for the formula to have size order h square. So unfortunately, I can't do constant size, but at least it only depends on h and not on my vertices. And then the third thing that I've given is this planar embedding. So I needed to talk about what on earth is a planar embedding. How do you give it? In the pictures, it was always just a drawing, maybe with some curvy thingies, but for purposes of algorithm, the way you give an embedding is that you fix at every vertex the order of the edges in which they show up around the vertex in this hypothetical drawing that, you know, we don't necessarily know yet. So all it is an order of the edges at every vertex, a cyclical order. The way I specifically will describe it here is not through the order, because that's a permutation, I don't know how to say that. Instead, I will describe it through angles. So an angle is just a part of that circle here between where it hits two edges. So an angle is described by two edges. And what I specifically want is this predicate is angle E1, E2, where the edge, the first listed one, comes before the next one in that cyclical order, which I am assuming to be counterclockwise. This is one of the places where the half edges are useful. I don't have to tell you which endpoint. They only have one endpoint. So this can only be an angle if they share exactly that one endpoint. Well, that's a planar embedding. It's given to me, so I assume that I have this predicate. All right, let's build the formula. Actually, we'll build it in pieces. What the formula will do is, as a first step, it'll quantify a few things. We already talked about the level assignment, which is just a coloring, which is just a vertex partition. So it'll quantify over all possible ways of doing it and try them all. But now that it has done that, I can derive all sorts of interesting things for my graph. That as soon as you fix the level assignments, I have to respect these. Let me explain this first. Actually, first, a disclaimer. I will assume I don't have horizontal edges. So there used to be an edge here between 2 and 2. And for ease of description, I will assume that I don't have such things. In the paper, we're aiming to do everything with horizontal edges. This is just that my definitions get a lot more complicated if I have to explain how I handle that if there's horizontal edges. So, right, let's not have horizontal edges. And one of the things I have then, this is one place where things get easier, is I very naturally obtain an edge direction, namely from the lower level to the higher level for every edge. Where do I go? So this leveling, the level assignment that I picked through simply existential quantifying over all possible ones, gives me an orientation of my graph. All right? The other thing that gives me is something called a flat angle. Remember we had angles between two consecutive edges? I'm going to separate out the ones where I have an incoming edge transitioning to an outgoing edge or the other way around. And those I will call flat. Doesn't have to happen. The rest of the vertices here are actually all sources or sinks, so they don't have both, so they don't have flat angles. But this one has incoming and outgoing, and so it has some flat angles. I can write myself a little helper function, helper predicate, whatever you want to call it, that tests whether something is flat. So these things will sometimes show up here in minor font and TT looking, just to sort of give you an idea. Yes, I can express that in MS. It's not a big deal. Right? Here's an important little result. It's completely obvious, but it's important. If I can respect these levels as you gave them to me, then my order of angles and who's flat cannot be arbitrary. What has to happen, remember I have a level assignment, so I have these edge directions which are supposed to follow the level assignment, which means all these outgoing edges need to go up, and all the incoming edges need to come from below, which in particular means that in the order around the vertex, the outgoing ones have to be consecutive, as do the incoming ones, which means you can only have two flat angles. So basically, if I don't have two flat angles at some vertex, no way this level assignment can work. So let's throw a little MS formula onto it that basically says at every vertex, please, do I only have two flat angles? So there. I can somehow express that in MS. All right, so now we have a level assignment, we have an edge orientation, we have flat angles. I want more angle labels. Sorry, but I want all those angles labeled. You will see it'll be useful. So I'm not a source or sink. We already have these two flat angles that I then have, assuming I can respect the whole thing, the whole level assignment that you gave me. All the others I will call small, and the reason I call them small is that they simply can't be very big in any drawing that respects the level you've given me because, well, between two outgoing edges, they both go up, so you have angle less than 180, and that's what I call small. So those are all small, that's easy. Things are a little weird at sinks, because if I look at an L-respecting drawing, then most of these angles are small. This is a sink source, but there's one that's big, and I want to call that large. And if you give me a drawing, you can immediately say, yeah, that's the large angle. The problem is you're not giving me a drawing, you're giving me a graph. And I have no idea who's supposed to be the large angle in this. But I will need large angles later, you will see. So who's large? Well, existential quantifiers to the rescue. Why don't we just try all possible ways of assigning large angles at sources and sinks? So what I will simply do is that remember, we are building this MSOL formula. We'll continue with basically saying, where are my large angles? I'm expressing it in a slightly different way because I don't really know how to talk about angles, but I do know how to talk about edges. So I'm going to pick edges. Some are green and some are purple. Remember, these are half edges, so this is two separate edges picked. And the rule is then that an angle is large if it follows a picked edge in the clockwise order, for which I please want only one at every source and one at every sink and none elsewhere, but that's all M is expressible. So the answer is I don't know who the large angles should be. I will simply try all of them. If I succeed for any of them, good. So now I have this now I've actually labeled every angle. Namely, I know who flat is, automatically from the edge direction. I know who large is from this edge set that I've picked, and everybody else is small. Why? Well, we will see. What I should also mention is from now on, M plus is a little bit more than my planar embedding. It's a planar embedding plus this choice of the large angles. And for directed graphs, that's actually been done before. We didn't invent this. This is a standard tool if you worry about a thing called upward drawing, which we will get to in a moment. So this choice of large angles is something that other people studied already. All right, where are we now? My formula has picked all sorts of things, picked in the sense of existential quantified. So now I have a level assignment, an embedding, and these large angles. And I want a planar drawing that respects all these things. I want a formula that says, can you find a planar drawing that respects all these things? This problem is called level drawing. And I'm attaching a fix because it's a fixed embedding situation. And stuff like that has been studied before. In particular, what has been studied before is a closely related problem called upward drawing, where forget the levels, just realize that these edges should all be drawn upward. And people have worked on that, and in fact, given me algorithms, characterizations, whatever. It's even a pretty old result. So we know exactly when we can do this. And there's a nice condition here, something about the small and the large angles. So in order to check that condition, we need to know who's small and who's large. So implicitly in there somewhere, we needed to know who's small and who's large. That's why I fought with those. So it's exactly characterized. So I certainly need that my MSOL formula checks these because this will be necessary conditions, right? But how? I see a lot of addition going on here. It's only +2, but I'm writing the number of small angles, so I need to count the number. Count? I don't know how to count in MSOL. And then the other problem, and this is also a big problem, I simplified the problem by dropping the level assignment. I can't do that. Even if I have an upward drawing, it may or may not fit the levels that I was given. So here, for example, okay, I was given that drawing, and by sheer chance, the levels mostly work out, at least if I add another empty level down there. So that would be fine, except there's this 1, 1 in the middle, and that really shouldn't be on level, what's now level 3. It should be on level 1. If I move it to level 1, then things don't look good. So sometimes you can adjust your upward drawing to respect the levels, but here that does not look good. What's even worse than that, and you don't see that yet, but I will convince you of it, I hope, that this phase cannot be realized at all, not with that level assignment. So even though it had an upward drawing, that's not sufficient, it's only necessary. I really need the whole thing of, does it have a level drawing? conveniently enough, somebody has studied before. You may notice that by sheer coincidence, that's my co-author, one of the two authors here. So Ignaz knew all about that result. There's a linear time algorithm for level drawing. So hooray, we can just test it, no problem. Anybody see a problem? What am I doing? I'm not building an algorithm, as much as I like building algorithms, but I'm not building an algorithm here. I'm building an MS formula. This is an algorithm. Algorithm is no good for MS formulas. As lovely as it may be, but I can't imitate what that algorithm does, at least if it's complicated enough in an MS formula. So unfortunately, that doesn't really help me. What we need is something that says this graph has a level drawing if and only if the following stuff is satisfied. And Ignaz looked at his own algorithm and went, I'm sure we knew it, but we never wrote it down, and he wasn't even sure what it was. So we had to prove it. So let's characterize when we have yes instances. For which we should look at this face again, where I told you you can't realize this face. What goes wrong in this face? What goes wrong in this face is that there's a little, my colors really went missing here, fine. These are all nicely colored in the original slides, but anyway. There's a path here along this face from 2 to 3 to 4, and as always, the numbers tell me which level I should be on. So in some form, you know, right or left or bend a little bit, but it more or less has to be drawn like that. Now, the other thing I also have in this face is that the angle at 4 is small. And we know what small means. Small basically means don't go over 180. So that means if I also want to respect this face, that this edge here has to come in from the left. It can't come in from the right, because then that angle would be over 180. So the edge, in any respecting drawing, has to come in from the left. That's what the small angle tells me. Now you look further at that edge that came here, and that came from level 1. So in particular, however it came here, it had to come from level 2 and even below that. And the same holds at the other side, where the angle at 2 is small, and it came from level 5, so in particular it came across level 4. And this is not looking good, is it? So you probably see a crossing. I don't see a crossing, I see a fish. So this face has a fish. Let me formally define what I mean by this face has a fish. We can find a walk along the face with u to v to w to x, so that all these levels work out. So I have all these levels assignments here. The other thing that I very much need about it is that the walk is required to stay within the levels. If I could ever go outside the levels there, I could probably get around here somewhere. But my walk has to be forced by the level assignment to stay within. And then the angles here should both be small. That's the example we've seen. There's another case where they're both large. That's just as bad. Basically, it's inside out for where the face is. And it's very easy to see that if you have a fish, then you cannot respect the input. Basically, you find a K33 somewhere there by adding a few things to your drawing. What took us a bit is to say, and that's an if and only if. So I have a level drawing if and only if no face has a fish. Or in other words, that's my characterization. I've successfully filled enough time with all the review of existing stuff that I don't really have time to talk to you about it, how I prove that. But actually, the proof is long but not very difficult. It all boils down to if you don't have large angles, at least not in the interior, then the upper drawing will work. And if you do have large angles, then I can somehow add in a new edge without creating a new fish. And add edge and add edge and add edge until there's no large angles left. And then I'm in the base case and I can draw that. So it's long, but it's not terribly difficult. One of the reasons why I don't want to talk more about that is that we're still having a hole here, because just because I have a characterization doesn't mean it's MS expressible. And that's what I really want to do, right? I want to build an MS formula for straight line drawing. So we need to express that. Luckily enough, if you are comfortable with MSOL, this is not hard. What is it that I need? I need this path. We saw in Hamiltonian path how you phrase there is a path, right? So all I'm saying is I want some subgraph that forms a path from u to v to w to x. And that can all be expressed. It needs to walk along a face, but I know where the angles are. And I know I can check whether there's an angle. So I can probably just check, for each edge along the path, is that an angle? There's a little bit of trickery involved here because I need to make sure I take the right angle and the right face and the right edge at the right place and half edges and stuff. Somehow it can be done. And then I need the levels to do what we want them to do. There were all sorts of conditions on the level. That's all arithmetic, but our levels are between 1 and h. And I convinced you earlier, I hope, that between 1 and h, I can do these kind of things. And then the last thing I need is that the angles are either both small or both large, but already in part B, I talked about all these angles, right? So I have these angles as I'm talking around there. I found them. I just need to add to part B that at V and W, these two angles are both small or both large. So that's all fine. I can express my fish, and we are done. Here's my formula. Well, really small written, and even the small written stuff is still using a lot of subroutines, so it would be pretty long. But roughly all what I want is I existential quantify on the vertex partition and on the indication of who the large angles are. I have some easy conditions that I need to verify, like it's a partition and every source has one and that kind of stuff. I need that I don't have more than 2 flat angles. I'm actually not entirely sure whether I need that, but I can certainly say it. I don't actually need the upward drawing condition. Turns out that if that's violated, then you have a fish somewhere. But that's not obvious. So all I need to otherwise do is to check whether the face has a fish, or none of them does. And all these things I told you before, we can somehow do. So in summary, okay, 2 steps that were a long time ago, Brad Niebuhr should remind me. We had Courcell's theorem that the tree width, if that's small, then that's all I need to be fixed parameter tractable. The other thing that I need is I need to somehow actually get myself the tree width. Luckily enough for planar graphs, there's really easy, really nice 5 approximations for the tree width. So that's not a big deal. I can compute the tree width. And if that's too big, abort. And if that's not big, then run Courcell's. And so I'm fixed parameter tractable in H. All right. Let me talk about a few other things. First of all, I worked on fixed parameter, fixed embedding, straight line height. We had the result by Dumovich, and we should probably compare the two. Now, theirs was a different problem. So in some ways, I'm comparing apples and oranges, but still it's probably interesting. How are we better? Are we better? Well, it's a different problem. Maybe we're better on the runtime. We're way worse on the runtime. Theirs was bad. Ours is horrible. Courcell's theorem, which we use as a black box, doesn't even state what that function is, but it's really terrible. The reason why I'm not too worried about that is that once you have a problem phrased in MSOL, it's usually not too hard to do a direct dynamic programming in the tree decomposition. In our case, it would even be a path decomposition. So good chance that we could do direct dynamic programming. And because I'm not quantifying over all that many things. Remember, we only quantify with a vertex partition and a set of edges. That doesn't sound too terrible. I think it'll be easier to understand than the Dumovich et al. I just haven't had the time to really work out the details. So I don't know exactly what the runtime will be, but I think it'll be tolerable and perhaps even a reasonably easy to understand algorithm. But here's the main reason why I really worked on this. I want that this doesn't just work for straight line drawing. I wanted this for all sorts of graph drawing models. All right, let's talk a little bit about other graph drawing models. Let's start with one you've never heard of because I made up this name, but I called it a one up-down drawing. What is that? It's a straight line drawing, but for some reason, I want that every vertex has only at most one edge that goes up and at most one edge that goes down, which tells you right away it better have degree at most 4. But fine, I can check that. Can I check that? Well, all you have to do is into your MSOL formula, throw a little thing that says don't have more than 2 edges that come from below, and don't have more than 2 edges that come from above. That is really easy to express if you have your level assignment. But we are fixing the level assignment in the beginning, so I just need to add this one and the corresponding one with no 2 edges from above to my MSOL formula, and then run the exact same machinery, and I can find a minimum height. One up-down drawing, minimum height in linear time for constant h. Why do I care about one up-down drawings? You might have heard of a rectilinear drawing. It's a one up-down drawing, except I also want that everybody's horizontal or vertical. Can we do that? How do you phrase vertical? That means we're talking about x-coordinates, which you may have noticed the x-coordinates got completely lost in this whole approach. We're never talking about x-coordinates. Everything's implicit somewhere there. Well, good news is that it actually turns out that I don't need to do that separately. It turns out, and I proved that quite some years ago, that it's the same thing to have a rectilinear drawing of height h and a one-up-down drawing of height h. The two things are actually equivalent. You can probably kind of see it. I can kind of bend things around so that they're nicely horizontal and vertical. So good, no worries. Also fixed parameter triangle. But I really wanted to talk about orthogonal drawings. What is orthogonal drawing? Suddenly I'm no longer straight line. I'm allowing my edges to be polygonal chains that can bend around, but still everything should be horizontal or vertical. And you see right away, well, I have that if I have some subdivision that has a rectilinear drawing. So now you just have to somehow fiddle into your MSOL formula the concept of there exists a subdivision of my graph. This is where I really have to defer to Ignaz. There's a thing called MS transduction, and you can do it. But don't ask me what an MS transduction is. I do kind of understand, but I really don't want to explain. In the same spirit, all sorts of other drawing thingies. For all of these, we can answer the question, is there one of height h in time, fixed parameter tractable in h? All right, how about variable embeddings? I'm almost out of time and we will get kicked out, so I will just go over that. The short answer is it can be done, and it's really painful. But lots of details missing. Let me end with some open question. One is this runtime thing. It would be lovely if the runtime were ordered 2 to the h, because then I could do it for as much as h up to log n. That would be great. Can we do that? I have no idea. We have a couple drawing styles that we didn't do yet, mostly because the vertices suddenly no longer are points. There are graph drawing styles where the vertices are represented by polygons or something, and suddenly we're having a real hard time expressing that in MSOL because it's no longer a vertex partition. So approaches here failed. We have work to do. And then the last one is I really would like something for non-planar straight line drawings. Can you minimize the height, or can you at least prove that it's NP hard? I still don't know, not even for non-planar drawings, that minimizing the height is NP hard. But unfortunately, the entire approach falls apart because even if you have height 2, your path width could be very big. Think K2n, KNN, which you can draw on 2 lines quite easily, straight line. But the path width is rather big. So unfortunately, no idea, and this is for future work. Thank you for your attention.